Hello, we are the team Electronics for Musical Applications, and our project is creating a music synthesizer with FPAAs. The following video serves as a presentation, user guide, and demo for future senior design teams to continue our project. With that, the goal for our team this past semester was to leverage the FPAA technology created by Dr. Hasler to create a low-power analog music synthesizer. This is done by linking the synthesizer programmed into the FPAA to a MIDI interface which would output sound through a speaker. Unfortunately, due to COVID-19, the MIDI aspect of this initial goal was unachievable. Instead, we focused our attention on programming the FPAA with appropriate blocks such that when linked together, a viable synthesizer is achieved.
Throughout the semester, our design group worked with the System-on-Chip Field Programmable Analog Array, or FPAA, designed by Dr. Hasler's research group. The FPAA presents a technology that offers configurable and programmable design solutions in both analog and digital areas. The board consists of a microprocessor, SRAM memory, and circuitry to interface with analog and digital configurable blocks. With these features, the FPAA offers a low-power, configurable solution to analog designs, which aligns with our group's interest in creating a scalable and portable music synthesizer. Several elements of our synthesizer are able to be created and executed on the FPAA via RASP Tools software. With RASP Tools, designs are created with drop-in modules from a library of circuit elements. Inputs and outputs are routed to appropriate modules and I/O pads, and the design is compiled. Next, data is taken to set certain DC voltages and other parameters in the design. Following compilation, the software interfaces with the FPAA via USB and programs the board with the new design. With the previous steps completed, the board is now in a state ready to execute the program design. Another useful feature of RASP tools is the ability to create macro blocks for the ease of use and hierarchical designs.
Our original high-level approach involves sending MIDI information from a keyboard onto the FPAA's MSP430 microprocessor. The MSP430 would be programmed to convert MIDI data into a set of biases for a voltage-controlled oscillator, or VCO. The VCO would generate a square wave, triangle wave, and sine wave with the frequency of the note it was given. This waveform would be fed into the voltage-controlled amplifier, or VCA, which would modulate the waveform's amplitude with an attack, sustain, delay, release envelope, creating a realistic-sounding fade-out effect. This waveform would be fed to the voltage-controlled filter, or VCF, which would alter the note's timbre by slowly changing the cutoff frequency via the low-frequency oscillator. The resulting waveform, formed via subtractive synthesis, would be outputted as audio. We later modified our design to be an additive synthesizer. Instead of one VCO, we devised a bank of VCOs that were preset to produce certain notes. This would allow for playing multiple notes at one time. These oscillators' waveforms could either be passed or hindered by a set of T-gates routed directly to the FPAA's GPIO pins. The selected waveforms would be added via a summing amplifier and then fed to a VCA, which would provide a sort of volume control for the final waveform before it is fed through to the speaker.
For our voltage control oscillator, we tried a couple of different designs, which are both based on a ring of current-starved inverters and operation transconductance amplifiers. A current-starved inverter is an inverter with extra cascading MFET and PFET. The I/O pad 1 is the input of the inverter, and I/O pad 2 and 3 are the bias voltage for the PFET and the NFET. Increasing the bias voltage for the PFET and lowering the bias voltage for the NFET increases the drive resistance and the delay. In our design, a square wave is put through the CSI to create a triangular wave. The first oscillator was designed to output a square wave at I/O pad 5, with I/O pad 1 providing PFET bias voltage and I/O pad 3 providing NFET bias voltage for the current-starved inverters, and the DC voltage providing the reference voltage. A triangle wave was expected at the output of the CSI after the I/O pad 5, but we were unable to produce a triangle wave. The first oscillator was tested with 1.7 volts for the reference voltage and 1 microamp for the operational transconductance amplifier bias currents. The bias voltages were swept from 0.5 to 2.5 volts. As the PFET bias voltages for the CSIs were decreased, the square wave frequency was increased and the amplitude was decreased. As the NFET bias voltages for the CSIs were decreased, the square wave frequency was decreased and the amplitude was increased. The second oscillator is a smaller version of the first oscillator and was designed using a macro block instead of microglyph. It forms a ring with two OTAs and a single CSI in between. It outputs a triangular wave at IOPAD 5 with IOPAD 1 and 3 connected to PFET and NFET bias voltage. The second oscillator was tested with 1 volts for the reference voltage and 2 microamps for the operational transconductance amplifier bias currents. The P bias voltage for the CSI was swept from 1.2 to 1.8 volts and the N bias was swept from 0 to 2 volts. As the PFET bias voltage was increased, the frequency was increased but the amplitude decreased. As the NFET bias voltage was increased, the frequency increased but the amplitude became too small. For future works, exploring and testing different bias voltages for the oscillator design is needed to thoroughly characterize the device. Different bias current for the OTAs should be tried and its effect on the waveform should be tested. Also, more IOPADs can be added to the circuits to apply different bias voltage to each CSI instead of applying the same voltage to all of the CSIs.
This layout is what we use to test our voltage summer. As its name implies, it takes two waves and adds them together. Our design features two inputs being amplified by OTAs and outputted to another OTA that is simulating a resistor. The idea behind using the summing amp was to choose which tones to play and combine them in case multiple notes were being played at the same time. In our testing, we were successfully able to sum two signals with all OTA bias currents set to 10 nanoamps. Future teams should expand on our design by testing with up to 12 input signals. These signals will represent the 12 notes in an octave. Different bias currents should also be tested to keep the resulting waveform within your design specifications.
One of the most important abilities for a synthesizer to have is the ability to amplify and change sound. You can do this by giving waves unique shapes and envelopes, or by simply amplifying it by a constant. The simplest way to achieve this is through multiplication, which is why we can construct a VCA, or voltage-controlled amplifier. Now, in keeping with the idea that this presentation should be a reference for future groups, I'm not going to delve too much into how the VCA actually works, and instead I'm going to focus more on our team's design, how future teams can use that design, and how they can build off of it. But just as a quick explanation, the VCA uses combinations of differential pairs to produce an output with the behavior of the equation on the right. And at low voltages, the hyperbolic tangent function just takes on the value of its argument. And if you set V2 and V4 to 0, you just have a multiplier. And new teams can read the textbook mentioned below to learn more about it. Now, the VCA is not as intimidating as it looks, and a large part of it consists of current mirrors like these. And so, in keeping with the principle of hierarchical design, the first thing we did was to design subcircuits of these current mirrors. So here are the cab designs we have for our PMOS current mirror on the left and our NMOS current mirror on the right. And here's the actual file for the cab of the P mirror. As an aside, cabs are useful alternatives to BLIFs when programming the FPAA because they represent the actual divisions within the FPAA, and they're faster to program and they're more efficient. Every cab has all these actual components inside, and you can just click on any node and just type in C to connect. You can also use the inputs or outputs of
unused capacitors as useful connections.
So once we finished creating the cab blocks for our PMOS mirror and our NMOS mirror, we just incorporated them into our larger VCA BLIF designs. On the left, you can see the VCA circuit with the subcircuits incorporated, but it's a little harder to compare to the schematic. So on the right, we have the transistor level design without the subcircuits, and it's the same exact design, but just a little easier to see.
And here is the actual file for the BLIF design of our VCA. I'm going to go over how to control it so that you can use it as a quick reference in the future. DC voltages going into this join block and going into this NFET are actually just ground, and they're used to set voltages V2 and V4 to 0 in the equation I showed earlier, so that way you can make this behave like a true multiplier. This DC voltage, however, is really crucial. It controls the I bias value, which is a scaling factor to the output. So I'd recommend you just leave it on at 2.5 volts, but you can actually decrease it to decrease that current. And the other bias that you should consider changing to get different outputs is the bias current to the OTA at the end. Actually, the output to the VCA is a current, so we added an OTA resistor to convert the output to a voltage. And if you choose a really high bias current for the OTA, you can actually drive part of the output to ground. So I'd recommend using a lower value, like 5 times 10 to the negative 7th. And IO pads 1 and 3 simply refer to the voltages 1 and 3, which you multiply, and the output should go to iPad 6.
When testing the circuit at different bias values, you can vary the amplitudes and frequencies of the inputs using the analog discovery tool and connections to the GPIO pins on the FPAA. At an NFET bias voltage of 2.5 volts and an OTA bias current of 5 times 10 to the negative 7 amps, we were able to produce amplitude modulation when multiplying two sinusoids, which is a good indication that the circuit is behaving correctly. While it's nice to be able to multiply sinusoids, the real utility of the VCA lies in its ability to create unique envelopes for sounds through multiplication. So I'd like to recommend that future teams take this design further by creating different envelopes for the VCA. One of the most useful envelopes that they could use is the ADSR, or Attack, Decay, Sustain, Release, which is produced by the circuit on the left. This circuit is simply a CSI, which normally produces triangle waves, but with a control NFET to be able to control the slew rate and create a sustain phase. ADSR is really useful because you can create a wide variety of sounds with it. For example, really sharp attacks and releases can produce really harsh loud sounds, and really long sustains can create unique creaking sounds. So I'd really strongly suggest this circuit for future teams as a way forward, and if they want, they can find more information about it in Nice's paper.
We hope you have enjoyed our demonstration and presentation on the music synthesizer with FPAAs. Our website is up and running and can be reached at this address. Here you can find any additional resources on what we have done, including more information on electronics for musical applications team members, project deliverables, and a link to the XCOS files for our designs.